I'm not the only computational linguist at UA, so it's very good to be here. So today I'm going to talk about coreference resolution. Can you guys tell me how many of you know about coreference resolution? What is it? Yes, close enough. All right, so I want to give a small introduction. It's going to get more detailed later on, but basically coreference resolution is the task of clustering together expressions, textual expressions, that point to the same real-world entity or event. All right, so here's one example. So if you look at Michelle Obama's Wikipedia page, the text says something like this, right? And basically, coreference resolution does the job of linking she with the full name, right? They are both textual mentions, and they both point to the same real-world entity, right? Obviously. That's it, basically. That's the task. Why should you care about it? Well, there are many end-user applications that actually use it. So question answering, like answering questions, who is Barack Obama's spouse, you cannot answer it unless you have coreference resolution, because typically the systems focus on one sentence, right? So maybe using this sentence, they find out that Obama is married to she, right? But if you don't know what's the actual entity behind the pronoun, you cannot answer the question. Same application, but phrased a little bit differently. It's called information extraction, where you want to extract all the spousal relations from a very large document collection, right? So it's exactly the same problem, but phrased differently. Instead of focusing on one person, you want to extract all of them. So again, if you don't have coreference resolution, you can't. And use aggregation, right? What are recent events involving Michelle Obama, right? So this involves cross-document coreference resolution, when instead of having a single document, you have multiple documents. And I'm going to talk in a second about that. But basically, if you don't understand that these two names, Michelle Obama in one document and Michelle Obama in another document, point to the same person, you cannot link them. And that's a big problem, right? Because, well, before we talk about that, there was a paper a couple of years ago at ACL, which is the main computational linguistics conference, where a group of folks from BBN showed that performance actually doubles for these applications if you employ coreference resolution. So it's very important, right? And I'm not going to say too much about machine learning, but let's survey a very typical algorithm for coreference resolution first. So the typical algorithm takes a piece of text and identifies mentions in it. Mentions would be nouns, pronouns, maybe verbs if you're looking at events, right? So basically, textual fragments that look like they might point to an actual entity or event. Once you have this, you basically take all the possible pairs and compute a score. How likely it is that these two mentions point to the same entity. So you essentially want to decompose the problem into a binary classification problem. You take two entities. Are they part of the same entity or not? Right? And you assign a score, right? So the width of these lines, in my case, indicates the confidence. So I'm confident that this belongs to the same entity, whereas here I'm not so confident, right? So you essentially end up with a graph. Once you have this graph, use a partitioning algorithm, pick your favorite partitioning algorithm, to break the graph into clusters, right? And each cluster corresponds to an actual entity or event, right? So she and Michelle Obama would belong to the same cluster. This is very, very typical. If you look at the literature, I'll say over 90% of the papers do this. Right, so we learn a few things from this work. Most algorithms focus on step 2, computing the pairwise scores between two mentions. Right, but that's a problem, because that's a local representation of discourse, right? You only look at two mentions, and you ignore everything else in the document. You don't know what's happening with the other mentions in the document. So that's not ideal. And recent work has shown that it's actually important to model coreference resolution as a global task, where you model all the mentions jointly, right? But this gets harder and harder to do with machine learning. Furthermore, we found that machine learning models in the context of coreference resolution generalize poorly to new text, new domain, right? So if you have a coreference resolution trained on news documents, and then you move to sports documents, they're not going to work so well. And that's a problem, because annotating coreference is incredibly hard. Right? If you look at inter-annotator agreements for coreference resolution between humans, it's in the 70s, right? So they disagree on 30% of the cases. So it's a hard problem, so it's expensive. So the first idea I'm going to talk about in this work is we're actually dumping machine learning completely. So that's why I thought this presentation would be appealing to linguistics, because I'm emphasizing the linguistic aspect. So what I'm saying is that instead of machine learning, let's use a deterministic model based on rules or grammars. Right? Well, they're not actually grammars, let's call them rules. And more importantly, this approach follows a baby steps framework for learning, which means that we're going to take instead of applying all the rules at once, we're going to take multiple passes over the text and apply the rules incrementally. So we start with the rules we're most confident about, and then we move on in the list of rules. So what this does is it's incrementally accumulating evidence. And we use this evidence for the follow-up steps. And I'll show that this actually works very well in practice. Furthermore, this is a global model, meaning that once we have a cluster, and remember this is an incremental process, so we start seeing clusters very soon. And once we have clusters of mentions, we shared features and attributes of the mentions within a cluster. Right, so even if you have a mention that's underspecified in the text and you don't know, say, is it an animate being or an inanimate object, you may get it from a different mention. So you get additional information for mentions that belong to the same cluster. And I'll show again later on that this is actually very useful. However, entities are only part of the picture. So this is a very simple example where I'm highlighting the nouns in blue and the verbs in red, right? And of course, you can have events represented as nouns, right? Nominalizations of verbs, like campaign, right? That could be an event, actually, not an entity. But for now, I'm making the simplifying assumption that entities are blue and events are red, right? So if you just eyeball this, you see that there's a lot of red, right? So there are a lot of events in there. In fact, about a third of the words in the corpus I use are events. Right. And that's important because events are fundamental for cross-document news aggregation. Right, so if you have all the events going on in the world, right, I'm actually using one of the first applications developed for Romanian, and they do not do this. So I get the same news article 10 times when I look at my iPhone, right, because they don't aggregate news. Right, so they should do that, and most applications do. And in fact, it's a big business in the US, right? How many of you use any of this? Right. At some point I used all 5. Now I use 4 out of 5. So it's a big business, and there's lots of money and lots of interest in this. And the thing we found out was that first observation is that entities help event resolution. So if you look at these two verbs, placed and put, it's very hard to understand that they actually refer to the same event, right? But if you look at the arguments they have, right, New Orleans Saints and Saints, Reggie Bush and Bush, their context is exactly the same. So if you somehow knew that these two mentions belong to the same entity cluster and these two to the same entity cluster, you can confidently merge the events as well. And the reverse applies as well. Events help entity resolution, right? So if you knew that, this is easy, knew that this kind of looks like the same event, right? Some poor guy has hanged himself, then you can probably guess, or at least get additional evidence, then these two noun phrases point to the same person, right? Even though they're completely different. So basically, the bottom line is that coreferent events have coreferent arguments, right? That's the fundamental observation. Yes?
We understand events. How does the machine understand?
That's a good question. Let me postpone it for a second. The short answer is it doesn't, and it doesn't have to, because it's a transparent process where it's merging. The algorithm doesn't care if it's an event or a noun, or an event or an entity, sorry. It's the same algorithm that applies to both, and I'll describe the algorithm in a second. So that was actually one of our goals. So let me get to that. So the main idea is we want to do joint entity and event coreference resolution, right? Because they should help each other. The second thing, which I'm going to say later on, but I'll just mention it now, is that we want to do this transparently, because it's a very thorny issue, what's an event? Right? That was a very good question. I don't want to get into that. I'm not really a linguist, so I don't want to get into that. I want to merge things transparently, regardless if they're events or entities. So we have an algorithm for that. But first, let's talk about the first idea, the rule-based models. This is just for entities. So again, just as a summary, this is a novel architecture, and it uses baby steps learning, which means we're doing the accurate things first, and we move on incrementally through the set of rules that we have. It's global because we allow attributes to be shared between mentions that belong to the same cluster. And it's deterministic. It's very easy to understand. And in fact, this was the top system. So CONNEL is the Conference on Natural Language Learning, and every year they organize a shared task, which I really like. They focus on good things, usually. So in 2011, they did English Coreference resolution, and this was the top system in 2011. We did not participate in 2012, where they did multilingual entity resolution, Coreference resolution, sorry. But some other groups did, and they took our system and adapted it. And in fact, the top two systems use this system. So I'll say more words about that. Open means you can use whatever resources you want. Closed means you can only use the resources provided by the organizers. And I'll say a few words about what type of dictionaries we use and where they come from. So baby steps approach. So basically what we do, this is sort of a visualization. We have a set of sieves. Each sieve contains a set of rules. And each sieve is applied in a separate pass over the text. So we take the text, we take a set of rules, we scan the text once, and we build some clusters. Then we take another set of rules which have lower precision, and we scan the text again. Right? So this is the highest precision, the ones we're most confident about, and this has the lowest precision but highest recall, which means they have better coverage. Right? This is a very simple system, so once you pass with a set of rules over the text, you cannot modify it. You trust each layer completely once you get it. It's very simple, and it's modular. In fact, it's very easy to add your own module in here, and that's what two groups did in 2012. This thing, we called it baby steps framework, is actually very common in machine learning, in computational linguistics, in cognitive science. It's called in many different ways. I've seen it as shaping, I've seen it as cautious learning, I've seen it as scaffolding. So it appears in many different ways. And in fact, Peter, who's a postdoc that joined our group, gave me an example from hardware. So Peter builds 3D printers. And in fact, he built one that was simple enough such that he could actually build parts for the 3D printer itself using the printer. Right? So you build a printer that's simple enough, but it's good enough to build parts for the better printer. So use the printer to improve itself. So that's essentially baby steps or scaffolding for hardware. So here's the architecture. So we start with mention detection, which basically looks at the text, and we highlight everything that looks like a mention. It could be a pronoun, could be a noun, and that's typically it for this phase. We'll extend it to verbs later on. And here we focus on high recall. We tag everything that might be a mention. And we'll see later in this step how we drop things that are not actually mentions. And then we apply the sieves. We currently have 11 layers in our system. And we apply the sieves incrementally, and as you move down the list, the recall increases, which means coverage increases, and precision decreases, of course. You usually have a compromise between the two. What's important is that as you move down this list, you can make more and more global decisions. What I mean by that is that as soon as you apply one of the sieves or more, you start having clusters. And as you start having clusters, you can have global information shared between mentions. Right? So you can have a cluster that covers one entity over the entire document. And that gives you a lot of features that you didn't see for each individual mention. So as soon as you apply this, you start having clusters which allow you to take global decisions. So here's one intuition. Why is this useful? So let's look at, just for simplicity, look at 3 mentions. So This is what our system did when we tried to extract attributes of mention. So we have the Israelis, right, the people of Israel. We have Israel as the country and we. Right? So for the Israelis, the system understood that it's a plural noun. Animacy means, is it a being? Does it have a soul? Right, that's what animacy means. Or an object. Right, and it's unknown. It doesn't know because it doesn't know if you're referring to the people or if you're referring to the country as a geopolitical entity. Right, so it couldn't make up its mind, and it says unknown. It's a wild card. It could be anything. Then we look at we is easy. We know it's a being and it's plural. Israel, this is the country. Right, so we know here it's the country, so it's singular and inanimate. Yes? Could be, but this is the actual output of the system. And it's, yes. Well, it's unlikely to be, yeah, go ahead.
So you had a sort of simultaneously working on events and things.
Yeah.
Is it just those two? Because it would seem like you could sort of, say, work on time references at the same time.
It's just entities and events for now. So temporal resolution is a different problem. I didn't work on that. So you could...
But the hypothesis is it wouldn't help.
There is no hypothesis. I do suspect, at least theoretically, that it should help, right? So you may have exactly the same event, but if it happens at two completely different instances of time, it's a different event, right? But I didn't work on that. Yes?
Well, you say that the successive levels of analysis cannot revise what the previous.
Yes.
I understand it would be complicated to have that, but wouldn't that help?
Maybe, but it will complicate the system too much. So it's actually very, very simple. And it was built by, this system was actually built, well, through many iterations by a student who didn't really know anything about coreference. And it was still the best system in the shared task. So I think simplicity trumps some improvements you might get from, yeah, that's my philosophy. Anyway, getting back, yes? Yeah. Yeah, so that's also part of the feature in the system. But here I'm just showing a subset of the features that I care about for this particular example. But yes, you're right, of course. So a typical system would basically look at pairs of mentions. Remember the first figure I showed, right? So you look at these two, and these two. And typically, how close they are in the text is a big hint. So because these two are very close, and they're actually compatible, they have the same number, and the animacies are compatible, right? So this is a wild card, it can match anything. And they are very close in text. And in fact, we tried a few state-of-the-art systems, and all of them do this. All of them link these two, right? And it's wrong, right? So it's not the correct link, right? Instead, what our system does, the first layer in our system, or one of the first layers, has a very clear rule which links gentilics with a country name if they appear in the same document. Gentilics means descriptions of the people who live in that country. So if those two exist, it's very likely that they discuss the same thing. And that's one of the initial passes. So in one of the initial passes, we go through the text, oh, we've seen this, we link it. And because we linked it, the attributes change, because now the attributes are shared, right? So this becomes inanimate, because we're talking about the country, right? And the number, it's a union of, could be both plural and singular. And because of that, this no longer matches this. So we avoid making that incorrect link, because we had a higher precision sieve running first. So that's essentially the intuition behind the model. All right, so the first pass, mention detection, is actually very simple in this phase. We'll extend it to verbs later on, but for now, basically what we do, we mark all the noun phrases and pronouns. And there are some exceptions. We remove generic it pronouns, and we in fact remove dates, because I don't focus on dates. So it's not on the slides, but it's part of the system. The highest precision sieve that we have is speaker identification. So if you have a text like this, I voted for Nader because he was most aligned with my values. She said, we now know because it's trivial. It's typically trivial, at least in nicely written documents like news documents, to identify speakers. It's usually a quotation, some nominal or pronominal phrase, and a say verb. Right? So knowing that, you know that she would link with my and I, right? Because obviously you're going to have the first pronoun in a quotation. And also you have some negative constraints. Knowing that she is the speaker, you know that she can never link to neither. Right? So you have additional negative constraints that you can learn from this. This is very old. I've seen this in one of Jerry Hobbs' paper, I think, in early 80s. So it's not an extremely novel observation. Exact string match. So this is also very, very simple, and there's a funny story behind this. So basically, they match the same entities, the same mentions that have the exact same string formulation. So TWA matches with TWA, USA Air with USA Air, and Shahab 3 ground missile with the other one. So there is a funny story behind this. So in 2012, Dan Jurowski, who was part of this group, reviewed a paper for multilingual coreference resolution. And what those guys did, they took our system for English, they applied it to Arabic, and they reported the score in the 60s. I'm going to discuss the evaluation measure later on, but 60s is high. So he came back to me and said, I don't understand. Our system is designed for English. How can you get a score in the 60s for a completely different language? And it turns out that after discussing with the authors, this sieve was apparently really, really useful for Arabic. And obviously, this is language independent, right? You're just doing a string comparison in whatever language you use. It's not that important for English, but it's still important. So here, just to have an Arabic system, just compare strings. We also have something we call relaxed string match. So what we do here is we identify the head word. So every phrase syntactically has a head word, which is defined as the most significant word of that phrase, right? So for this one, Clinton, whose term ends in January, it's Clinton. So what we do here is we identify the head words, and we drop everything following, because that's usually a description. And then we do string match. So if you do that, then Clinton matches with Clinton. And then we have a series of precise constructs like appositions. Right? So if you know that this is an apposition, and parsers are reasonably good at that, then you know that Bob Gerson points to the video editor. Right? Predicate nominatives, which are defined by copulative constructions. So something be something else, right? Then there's a link between two. So this group is a leading force in the field. Right? Role appositives. So the whole phrase actress Rebecca Schaefer points to actress. Yes?
Sorry. So sorry, the system relies on like a full syntactic parse?
Yes. Yes. So we use the Stanford parser for this system. So real world syntactic analysis is available. So it's not perfect, but it's something. And there's a few more. We have relative pronouns. The final straight would be linked to which. Again, using syntactic information. We have a very simple algorithm to identify acronyms, simply by looking at the first letters in a sequence of uppercase names. So Agence France Presse is AFP. And the Gentilix rule I told you about before, so Israel is linked with Israeli. Then we look at head matches. So obviously you want to link two mentions if they have the same head word. But it's not only that. You want to link those two, but you don't want to link it with this mention. So basically the rule here says as long as they have the same head word and they match these constraints, then we link. And this is a very important constraint. So this constraint is basically sort of a discourse model. This constraint says you can never have new information in following mentions. Typically, especially in a clean text that's been reviewed by an editor, like a news article, usually the first mention that mentions something is the most descriptive, right? And we see it here: the Japanese company, blah blah, the company, right? So that's good. And this is a new entity. It introduces new information, the electronics company. Right, so you also want to have additional constraints. So here we look at locations. The location, if they mention locations, they have to be the same. You shouldn't have numeric mismatch. And not I within I. I within I is essentially a syntactic construct where you have two embedded noun phrases that have the same head word. Right? If they have the same head word, like Sony Corporation of America, is the same entity, so we just annotate the longest. Okay, so this is the same as above. So suppose we're trying to resolve this mention, senders. But now we allow it to match with any words in the previous clusters. So if you look at this cluster has three mentions: souls, the judge, circuit judge, and sender souls. None of these mentions has the head word senders, right? But in this sieve, which has lower precision than the previous one but higher recall, we allow head words, the head word of this mention, to match any words in a cluster. So it matches senders, which modifies souls here. And lastly, we conclude with pronoun resolution, which is a typical Jerry Hobbesian system where we essentially look for matching attributes. And here we use all the features that you'd expect: number, gender, person, and animacy. And we detect this using part-of-speech tags, named entity labels, and we also have a dictionary for gender and animacy that was developed by Bergsman, Lin, and Jian Lin. All right, so finally we have post-processing. And the most important step is that we discard singleton clusters, meaning clusters that have only one mention. That means that mention doesn't point to anything. And that's why in the first step where we look for mentions, we could be very, very inclusive. Anything that looks like a mention is dropped in there, because if the system doesn't link it with anything else, we're going to discard it here. And this is just constraints. This is the annotation standard in the Ontonotes corpus. I don't know if you're familiar with that. It's essentially a new corpus that annotates syntax, named entities, semantics, and coreference across various genres, like news, blogs, emails, and something else. So for some reason, the standard they used is that they do not annotate appositions, and they do not annotate copulative relations. All right, so we discard those at the end. All right, so let's look at one example. I think it's always clear if we have one. So, this is an artificial text, but it has most of the stuff that I care about. So John is a musician. He played a new song. A girl was listening to the song. It is my favorite, John said to her. All right. So the first step is mention detection, right? This is everything that looks like an entity mention, right? All the nouns and pronouns. Right. In the next step, we do speaker identification. So now we know that this is the speaker. And we look for first-person pronouns in the quotation. So we have a link, John with my. Then we do string match. So now we have John with John. They're identical. Then we have precise constructs, and we have two copulative constructions here, right? John is a musician, and it is my favorite, right? So it and my favorite will be linked as well. Then we have strict head match, and I think this links a new song with the song, right? So as you go through the text, you see that this phrase does not introduce new information, right? It doesn't have additional modifiers, so it's okay to link them. And then we have pronoun resolution, which does everything else. So it is going to be linked with song. A girl is going to be linked with her. And that's it, right? And then in post-processing, we're dropping the copulative constructions, right? Because they were not annotated in the corpus we use for evaluation, right? So we're dropping musician and we're dropping favorite. Okay, before we move on to results, this is actually important. So you get your text and you have a bunch of mentions. Which ones do you actually use for coreference? So another observation we had was that, let's look at this. It's always important to consider only the first mention in textual order in any given cluster. What I mean by this, suppose this is the text, and we're somewhere in the system, right? So some sieves were applied. So we do have some partial cluster information, which is indicated here by colors. So these two mentions are in the same cluster. These three are in the same cluster, right? So we scan the text essentially left to right, and we only look for the first mention in each cluster. Also, another detail is that we're only looking for candidates to the left of each mention, right? So since this is the first mention in the document, there's nothing to solve there. So the first mention we're actually looking at is this one, right? This one has a candidate, so there's some work left to do, and it's the first one in the red cluster. So we're looking at that. This is not the first one in the red cluster, so we're skipping that, and we're moving to the green one, right? That's the first one in the green cluster, and that's it. Right, so you see how this reduces the search space significantly. Instead of looking at 6 mentions, we're only looking at 2. Right. Not only it reduces search space, it improves your chances, because if you just look at the first mention in the cluster, practically that's the one where you have most of the meat, where you have most of the descriptive terms. Yes?
The green seems to be a symbol.
Well, correct. Correct. Correct, but this is at some state in the system, it's not at the end, right? So far we don't know if it's a singleton or not. You may look at it and say, well, this is actually part of the blue cluster, in which case it changes its color to blue. Okay, this is why I call the system a global system. So once you have a cluster, we have, instead of having a single modifier or set of modifiers, we have a pool of modifiers. So all the modifiers of all dimensions get dumped into a pool of modifiers. We get a pool of head words, and we have a union of attributes, as we saw in that example. We have number, gender, animacy, and so on as a union. So that gives you some robustness to missing attributes or incorrect attributes. Remember, this is a system that's not perfect, so it may decide that an attribute has the incorrect value. So here's one example where it's actually fixing the incorrectness problem. So if you have a group of students, our system decides that the number is singular. Right? That's obviously wrong, but this is what the system decides. And then you have 5 students, here the number is plural. But after they are assigned to the same cluster, the number becomes singular and plural. So it allows you to match with any of the possibilities. So it's essentially recovering a little bit, yes.
I thought you had at some point you had a rule telling that when you check compatibility on this kind of thing, like a number.
Right. So yeah, this is an
Where this date?
the compatibility of numbers is in the last sieve number 11. So there, if they cluster together before that sieve, then it basically bypasses that rule.
The sieve actually, each sieve just pulls things together. You don't never have a sieve that
No,
cuts.
no. Exactly. Yeah, it's essentially a greedy system. It keeps clustering things in a greedy fashion. All right, so let's look at experiments. So people keep reporting results on this corpora, even though they're kind of old. So we did the same thing just for comparison purposes. And I grouped the systems into 2 categories. These are unsupervised systems, and these are supervised systems which use machine learning. This is sort of a very loose interpretation of the term unsupervised. I mean, yes, we did not use machine learning, but we had a bunch of people looking at the data and coming up with the rules, right? So it's humanly supervised, right? It doesn't use machine learning, but I use the unsupervised term loosely here. Regardless, it's a very simple system, and it still performs the best in most of the corpora. If it's not the best, it's very close. Right. More interestingly, these are the results over at the Connell 2011 shared task. And before we get into the actual values, this is the evaluation metric they used. So one interesting thing in coreference resolution is that it's very hard to evaluate the quality of a cluster. And there are multiple competing metrics to evaluate that. And it's debatable which one is best. So I do think that each one captures different things. So none of them is perfectly good, but none of them is perfectly bad. And the organizer came up with the same conclusion. So what they ended up doing was they did an average of 3 metrics. Right, so this is the score you get. So our system is the red one, was the best. The systems in dark blue are universities from the US. The systems in light blue are universities from someplace else. And well, the point is we were the first. And you see how the performance drops from basically 60s, high 50s, down to 30s. Closed track means we only use the dictionaries provided by the organizers. So the organizers provided some dictionaries with gender information and animus information. And during this evaluation, we only used their information. We didn't go outside for knowledge. There is an open track, and we participated in that. We essentially didn't use a lot more. We used 2 additional dictionaries, a slightly larger one for gender and a slightly larger one for animacy. So our performance didn't change much, and we're still the best. In 2012, the task was extended to multilingual coreference resolution. And there were 3 languages, English, Chinese, and Arabic. And it was a higher barrier of entry. So there were only 16 submissions versus 23. It's much harder to build systems for 3 languages than just for English. But there was significant progress. So the performance for English increased from 58 to 63. That's big progress. But 2 out of the top 3 systems use our system. So there was a system from IBM Brazil, who essentially took our system, and then they used a machine learning model to re-rank the candidates we proposed. But they got essentially their search space was heavily constrained by what our system produced. And they improved our system by about 5 points using this technique. And Vincent Ting group at UT Dallas took our system, and they essentially added 2 sieves. So this proves that our system is modular. They added 2 sieves. At least one of them was based on machine learning and was the best system for Chinese. So it essentially proves that our approach is multilingual. More interesting for this work is to see how much we get from our contributions. So the first contribution was sharing features across mentions in the same cluster, right? This is why I call the system global. So the system which shares information across cluster, a cluster becomes an entity. So this is called an entity-centric model. Gets close to 60 point score. The one which doesn't is 55 point something. All right, so we get about 3 to 4 points improvement simply by sharing attributes between mentions in the same cluster. So I think that's good. The second contribution is the multiple sieves, right? The baby steps architecture, and we get an even higher contribution here. So this is the regular system, the one with the sieves. And this is the system where I had a single pool of rules. So we scanned the text once, and the first rule that matched was allowed to cluster mentions. And we get about 6 points improvement here. So this incremental approach is very, very useful. Just as a curiosity, we looked also at the individual contribution of features. And here we remove number information. Here we remove gender, animacy, and named entity information. So you see that the number is the most important one. The score drops about 3 points. Everything else counts a little bit. It's interesting to note that animus is actually very important. I think this is novel. I haven't seen this anywhere else. It's about a point or more. Let's do a quick error analysis. So if you look, we looked at about 100 errors that our system generated. And it turns out that most of them, the largest bulk, was actually very complex semantics or discourse representations. So let's look at one example. So we have this text, new pictures reveal the sheer power of the terrorist bomb. In these photos obtained by NBC News. So this is complex in 2 ways. First of all, the headwords are different. Although I suspect if you look at the dictionary like WordNet, you may find that they belong to the same scene set. But more interesting, the discourse is weird, right? So there is new information introduced in the later mention, right? So we find later on that these photos were taken by NBC News. Right? So that breaks our initial assumption that there's no information introduced later on. Pronoun resolution is still hard. It's still a hard problem. So here we do a bad job on its, and I think we link it to land. Right? It's still compatible. It's third pronoun. It's inanimate. So it's compatible with land, but it's wrong. It should point to the ANC. There are sort of a lot of mentions that are actually non-referential, right? So this is a generic you pronoun. It's just a rhetorical statement. There are event mentions. So support the troops, not the regime. That's a noble idea, blah, blah. So that is actually an event mention, right? It points to the whole supporting the troops event. All right, so this is the first part of the talk, the longest one. So basically, I'm proposing a novel architecture for coreference resolution. And the baby steps, I think, is a major contribution. Also, the fact that the model is global. And also, it's interesting that it doesn't use machine learning at all. And it still obtains state-of-the-art results. All right, so let's move on to event coreference. So event coreference is essentially a cross-document, what we do here. And if you have a bunch of documents, we're trying to cluster things around events. So we need to know that announced and announced are actually the same event. We're also doing entities as well, so we need to know that AMD is the same as advanced micro devices, and so on. And the observation I made before was that entities help events. Right? So knowing that those two entities are the same helps us cluster placed and put. And the reverse is also true. Events help entities. Right. Okay, so goal is we want to have a holistic approach that resolves entities and events jointly and transparently, because I don't want to open Pandora's box on what's an event. Right? So I want to deal with nouns and verbs consistently. So research questions: can we actually prove that entity information helps event resolution and vice versa, and which features and model are best? So the funny thing is that most literature focuses on entity coreference. It's very hard to find papers that focus on event coreference. There are a few. I'll say more about this paper in a second. And we only found one that does the problem jointly. And it focuses in a very narrow medical domain. So this is essentially a new field. So here's the architecture. So in the first step, we do document clustering, which is essentially detecting the topics in the collection. And that's important because conceptually, you want to run this at the web scale. Right? So if you take a collection as large as the web, you cannot compare all the noun phrases and verb phrases across the web. That's impossible, right? So you want to reduce the search space into topics. And once you have a topic, you only search within the topic. You don't go cross-topic. So that was one of the first observations. The second one, we do mention extraction. I'll say a few words about that, but it's very, very close to what we did in the other system. And then we essentially apply the previous system. We apply all the sieves from the previous system to essentially cluster entities without pronouns. I'll get back to pronouns. And then once we have clusters of entities, we use those clusters as yet another implementation of the baby steps framework to cluster it incrementally events and nouns. And now the focus of this talk is going to be here. And at the end, simply because so far we focused only on nouns and verbs, we add the pronoun sieve from the original system. So basically, this system uses almost the entire system from the previous part of the talk, but it has another module here, which basically has implements that observation that entities help events and vice versa, and has a clustering module at the top. So document clustering essentially reduces search space. Right? But it does another thing. It essentially provides word-sense disambiguation. Right? Because once you have topics, you may have verbs in different topics mean different things, right? So hit in a earthquake topic means something else than hitting in a criminal report. right? So it does two good things. And we use a non-parametric clustering model. I'm not going to go into the details. You can use any clustering model you want. We just had that one available. Yes, well, how close the vectors of words are. But it's basically a vector space model. Yeah. So I'll just show the output of clustering. So basically this step clusters together these two documents and these two. Right, so this is some natural disaster, this is some financial report. They cover the same topics, but it still doesn't know what the links are inside. Mention extraction is basically an extension of the previous system. We use for nominal and pronominal mentions exactly the same rules as before. And we added an extra piece of code to extract verbal mentions. So verbal mentions are basically all the words that start with, their part of speech text starts with VB, minus some auxiliary and copulative verbs like have, be, seen, and a few others. What's important here is that events do appear as nominal mentions, right? We saw campaign in the previous example, right? So it's very hard, I don't want to get into that, how to distinguish between nominal entities and event mentions. Right, so our system transparently handles entity and events mentions. The only information we use is their part of speech tag, right? But we don't make any claims, is this an event or is this an entity? So this level is essentially exactly the same system as before, minus the pronominal sieve. And the goal of this step is, again, to reduce search space. If you have this deterministic system that does a good job on entities, why not use it? And then you already have some clusters built in, right? You don't have to search for those again. And this is the meat of the system, right? So let's look at this. So this is, I'm just showing for reference. I'm showing the gold clusters. Assuming you had access to the ideal information, what would the clusters be, right? So this means that these three mentions belong to the same cluster. The green ones belong to the same cluster, and the blue ones belong to the same cluster. Of course, our system doesn't know that. Right, so what the system does, in the first step, it applies the high-precision sieves. And let's assume that it generates these clusters. Right, so you see that it's generally OK, but since these are high-precision sieves, they tend to be under-inclusive. Right, so instead of one cluster, it has three clusters here. Here it has two. And once in a while, it's over-inclusive, right? They introduce the green mention in the red cluster.
You cannot make up for that last.
No, you're done. So, but since these are high-precision sieves, they tend to make more recall errors, like these, instead of these. So we didn't see this a lot. Okay. What's happening afterwards is that once you have these clusters, these sort of initial clusters built, it computes the likelihood of merging within each possible combination. That's how it looks like this. Right? It generates all the possible combinations. And once it has those combinations, it finds out which one of these combinations has the highest score, and it merges that. And once you merge some information, we go back to that global observation, right? You can share attributes among mentions in the same cluster. So we regenerate the features once we merge things. So it's essentially three steps. We calculate the pairwise scores, we merge the best, and we regenerate the features, because we need to regenerate the features because we have at least a new cluster, right? So once we have a new cluster, there's more information to be shared. And again, this transparently merges nominal and verbal mentions. So as an example, suppose we found that the red link is the best. We merge that. Then we repeat the whole algorithm again. We found that that link is the best. We merge that. We found that that link is the best, and we merge that. And we stop. We didn't find anything with a score higher than 0. Yes? Yes. Yes. So basically this is it, right? But the key thing here is, how do you come up with a score here? Right? That's essentially the fundamental operation in the system, right? The rest of it is just a for loop. So let's look at that a little bit. So the first observation is that we need a regression model. You can't have a classification model because almost no generated cluster is perfectly correct or perfectly incorrect. You're usually in some gray territory where you've done some good and you've done some bad, right? So you can treat this as a logistic regression problem where you have good class, bad class, right? So you need a regression model where you have a continuous value which measures the quality of the cluster you built, right? So the way we measure this is when you implement a merge, how many of the links you introduced are correct? What's the ratio of correct links? So let's look at one example. So this is one state of the system at some point. And if we look at merging this cluster with this, if we did merge, then we introduce two links, right? We introduce this link and this link. And they're both correct, right? So the quality score, which becomes the linear regression outcome variable, is 1. Sorry?
How does it know they're correct?
This is training. So during training, it has access to gold information. So that's actually a good point. So here, even though it's still a baby steps approach, here we use machine learning. Whereas in the previous one, it was a baby steps without machine learning. Why the difference? Initially, this was done again as a deterministic system, but I'll get to the features in a second. And we found that we have too many features with numeric values. So it became cumbersome to model those deterministically. So in that case, we found it more advantageous to use a linear regression model. Anyway, let's look at one more example. So if we have these two clusters, if we merge them, then the score is 1 link is correct over 3, which is the total number of links, right? So the quality score that we get, which again becomes the outcome of the linear regressor, is 0.33. Right, 1/3. The second observation, which was important, is that we need a non-linear learning setup, right? If you treat coreference resolution as a batch problem, it means you generate all the possible combinations under the world, and you treat that as training data. Some of them will be good, some of them will be bad, but the total number of combinations is exponential in the number of mentions. So even though we've done a few things to reduce the search space, like clustering documents and applying the high-precision sieves first, you still have too many candidates. So you want to use a non-line model where you keep incrementally merging things and retraining the model. So that's essentially what we did. We basically reapply. So you have the model at a given state. We apply it, and we see what merges it does. And we generate training data only from those operations it actually performed. So the intuition from there is that instead of training from all the data under the sun, you train using the operations that the model is likely to do in the real world. And it's a linear regression, L2 regularized, and we repeat iterating over the corpus 10 times. Each time we call it an epoch. Okay, so let's look at features. So here's the first one. So we do a cosine similarity of vectors of headwords of two clusters. What I mean by that is, suppose you have this cluster, Barack Obama, President Obama, US President. If you extract the headwords, you get Obama, Obama, President. You can build a vector where you have the word Obama with the weight 2, you've seen it twice, and the word President with the weight 1. And you do the same thing for all the clusters you have, and then you just compute the similarity between these word vectors. No. No, we account for synonyms in one of the other features. I'll get to that. Here it is. So basically, when you do a merge, another feature that's generated is how many links are between wordnet synonyms, right? So if we merge these two clusters, hit strike, this is one cluster, with strike, join, and say, right? You introduce two links that are actually synonyms. You introduce 6 links, right? It's 2 by 3, right? So 6 links are created, and 2 of them are actually between wordnet synonyms. Hit and strike, those are synonyms, and strike, they're the same word, right? So 2 of the links are synonyms. Then we look at features extracting using semantic role labeling. I don't know how many of you are familiar with semantic role labeling, but basically, I see that as a step on top of syntax. So instead of looking at syntactic relations, we look at semantic frames, which are essentially who did what to whom, when, and where. So you have a predicate, typically verbal predicate, although it has been extended to nominal predicates recently. And you have the arguments of the predicates. Who's the agent? Who's the patient? What's the theme? What's the location and the time of the action? Right. So here we have, for the predicate bought by, we have arg0, which stands for agent. The agent is AMD. The patient, which is arg1, is ATI. Right. So for verbal predicates, which is, there is some context missing. So in my previous research, I built a semantic role labeling system for verbs. So that's what we had. So we had these features just for verbs, essentially. So we have these two, and for the verb acquired, we have the same two, right? AMD as the agent, ATI as the patient. So the feature essentially counts how many of these we have in common. And you can do that in both directions, right? You can do it when you're merging two verbal mentions, and you can also count how many predicates you have in common when you're merging nominal mentions. Right. It's the same thing. So this is just another version of this feature where you're counting by argument, by role label, right? So we're seeing arg0 would be agent. These are notations from prop bank, so don't worry too much about those. arg0 would be agent, arg1 would be patient. So we look at counts for specific labels. So if we look at arg0, then we have one in common, right? So the feature would be triggered with value of 1. Okay, this is essentially a data-driven way of computing synonymity or semantic relatedness, rather. They're not exactly synonymous. But basically what we do, this was called second-order distribution similarity. And what we do, given a mention, there was a distribution of De Canglin, who's one of the researchers at Google right now, used to be at University of Toronto, built a distribution similarity thesaurus from web data, where he looked at, I don't know if you guys know what distribution similarity is, but basically the main idea is if two words have the same context, they are most likely related. Right? So he came up with a metric to measure how related words are by measuring the similarity of their contexts. Right? So we found out that new is very similar to original, old, existing, current, unique, and so on. You see that a lot of these are actually synonyms or hypernyms, but you do get antonyms in there. There's no way to distinguish between synonyms and antonyms with this thing. So there is a caveat there. But basically what we do, we took his dictionary and we looked at the top 10 or so most similar words for each word in our mention, and we built an additional vector. So the mention a new home becomes new, which is the original word, and then the top words from De Canglin's dictionary, right? So original, old, existing, blah, blah. And then the second word, home, this is our word, and the top most similar words from his dictionary, house, apartment, building, and so on. So for each mention, you end up with a vector. And then we simply, when we merge things, we simply compute their cosine similarity again. Going back again to, yes? Are they ranked, you mean? No, we simply have, no, they're not ranked. So this is their actual weight in the vector, right? They get the same weight. So the value here is essentially their frequency, how many times we've seen home in this vector. Of course, you could weigh it, right? Since this is your actual word in the mention, you could conceivably say that it should get a higher weight than the words you get from the dictionary, but we didn't do that. That's a good point, though. And we do the same cosine similarity between vectors of attributes. Right, so attributes are number, gender, animacy, and named entity label. Is this a person, a location, or organization? So assuming you have this artificial cluster, systems and a pen, the vector of attributes would be you have the number singular once, the number plural once from systems, and the gender neutral twice. Right? So we generate the vector of attributes, and then we compute the cosine similarity between them. All right, so pronoun resolution is just the one as that we discussed before, and it's the same system that everybody uses since the 70s. Okay, corpus. This was interesting. So, like I said, almost nobody worked on joint entity and event resolution. So the first problem we had when we thought about this was, how do we evaluate what we do? And it turns out there was no data. There was a corpus developed by Harabadziu and Bejan at UT Dallas, which did a good job of annotating events across documents. So they annotated about 500 documents with 43 topics. So we took that corpus and we did two things. We reviewed their event annotation because we wanted to make sure it follows the same standard as annotation specification as ontanodes. So we made sure it aligns with ontanodes. And then we annotated the entities. So now we had a corpus that's cross-document, has both events and entities. And this is an example. Color indicates same cluster. And we built two baselines, sorry. So baseline 1 is the Connell model from 2011, the model I described previously, with an extra sieve for verbs. And we found out that for verbs, the best you can do with a deterministic model is simply matching the lemmas. It's very hard to do much better than that. Baseline 2 does a little bit better than that by looking at semantic role frames. And the idea is that we merge two nominal clusters if the headwords match and their corresponding predicates have the same lemma. So for example, you have two clusters here. Obama attended, the president was elected, and Obama was elected. So the headwords match. I think I even have an underline for that. The headwords match. The labels match, although they come from different mentions, and the predicates match. Right, so in this case, even though we weren't sure with a deterministic system, now we merge them because we have additional information from the semantic frames. And we do exactly the opposite for verbal clusters. We merge verbal clusters if they have the same lemma and arguments of the same word. And basically, this is done to see how much you can get from a deterministic model that uses semantic frames without the linear regression part. So here are the results. And the blue columns are baseline 1, which is essentially the deterministic system without semantic row labeling. Baseline 2 is the deterministic system with semantic row labeling. And baseline 3 is the full system. And we broke down the score for nominal and verbal mentions and all the mentions. So you see that all the time it's worth it if you model things jointly. So you improve both events and entities, right? Or to be more precise, you improve both nouns and verbs, right? Regardless of what they are. We did a little bit of feature analysis, and we found out that semantic row labeling is actually very important in the regression model. So basically, this merges two nouns if they serve as a locative argument for the same predicate, and they're both common nouns. This is what this feature means. Or if they serve as agents for the same predicate, and they're proper nouns. Right, so, and so on. So basically, 6 out of the top 10 features use semantic row labeling. And that's important because semantic row labeling is the tool that allows you to link predicates with arguments, right? So it's essentially the scaffolding that allows you to build the incremental approach where you pass information from nouns to verbs. All right. Quicker analysis. So pronoun resolution, just like before, is a big issue, still unsolved. There are semantics that go beyond role frames. So if we look at these two mentions, the forces killed at least 40 people, and the dead included blah, blah. Right? So it's very hard to link the dead with at least 40 people. Right? They don't match. They have different heads. They have different predicates and so on. So it's more complex semantics than what the model does. one limitation of my semantic role labeling system is that it does not do arguments of nominal predicates, right? So there are a lot of nominalized verbs, right, in language, right, like attack here, right? If you had that information, the attack on the school, knowing that this is the patient of the predicate attack and attack on some other school, our system would have merged them because they match all the features that we had for semantic role labeling information. But our system doesn't do nominal predicates. So we missed this link here. We didn't know that they are actually arguments on the same predicate. So because of that, we couldn't merge them. But there's recent work. So my semantic role labeling system trains on PropBank, which is work by Marta Palmer at UPenn. I think she's at Boulder right now, where she annotated verbal predicates. And then that work was extended at NYU to include nominalized verbs. So you could conceivably train a system and get better on nominal predicates. Okay, so second part of this talk was essentially a holistic model for cross-document resolution, and we showed that semantic role labeling is important, and you can still apply the baby steps idea in this context as well. And ultimately, joint modeling is useful. So I have two big picture conclusions. They're kind of obvious, but nevertheless. So understanding the problem is more important than machine learning. You can't just take a machine learning model and blindly apply it. As we saw in the first part of the talk, if you understand the problem, you don't even need machine learning in some cases. And model things jointly when you can. So I showed that in the second part of the talk. And this was work by our Coreference group at Stanford. So thank you to them. Just quickly, I'll self-promote a little bit. So if you want to do some research work, let me know. I work on semantic role labeling, building grammars for NLP applications. In fact, Kristen's going to help with that, and question answering. And I will teach ISTA 455/555 applied NLP. So if you care about things like this, you should sign up. And I found this, which found it funny, and I kind of feel like those scientists a lot, so I thought I should have it here.